Hello again, and tonight we're going to be starting the first of a series on solving problems. And what I think of as a problem is anything where there could be a better solution, but the better solution isn't being offered because it kind of removes some big revenue streams out of the picture. It makes you more self-independent, and therefore, um, you know, they don't want that to happen. But if you ask them about it, they'll say, I don't know what you're talking about. But it's once you see what's going on here, it's literally um, there is a better way. Why is nobody spending money on the better way? Why do we spend billions of dollars per year on um, fusion power that's never quite there yet? But we still spend billions of dollars because big corporations take in those billions of dollars and go, oh, we're going to need more billions next year and next year and next year. And ultimately, it's kind of a near impossible problem to solve. But anyway, so this is the first of a series of solving problems. We're going to talk about electrical power generation. And next week, we'll talk about propulsion. But this is my take on it. So the series is a series of these things. It's actually what I see as problems or constraints. Power, we're constrained by a grid, building permits, scaling limits, costs. What really needs to happen is it needs to be very extensible. We need to find a way to independently generate power so we're not tied to a grid. And we need an inexhaustible source that doesn't milk us for fuel. On propulsion, too many missions end when their fixed fuel supply is exhausted. We need to remove the fuel supply mission duration constant or constraint because right now it's everything that we launch is stuck with when you run out of fuel, it's end of mission. Communications. All of our communications, if you think about it, is based upon modulation of the electromagnetic spectrum. And we're kind of running out of steam in that regard, as if we want to send communications out to deep space, the data rate by the time you get to Pluto is not gigabits, it's not megabits, it's barely kilobits. So if you wanted to go to the next star and communicate back, first of all, it would be a few thousand years by the time it gets to you. And the second one would be the data rate would be a fraction of a bit per second. So we've got to find some way other than electromagnetic spectrum modulation to communicate. And it looks like maybe gravity waves are the answer, but we'll talk about that in a couple of weeks. And then the final one is probably the one that's most implausible by most people is transportation. We keep making highways wider and putting in express lanes and think about mass transportation and buses and subways and trains. And when the population gets large enough, none of that really works because everybody wants to go from their own point A to their own point B, but they have to all trunk down a shared path. And as soon as you have any sort of shared path, if the total number of people wanting to move keeps growing, the path is always going to be congested. So we need to find a way of allowing you to go from point A to point B without all the dots in between. But like I said, that's probably going to be the most implausible one to think about. So we'll postpone that one for a few weeks. Tonight we'll talk about power. So the solutions that I'll discuss, a lot of the technology for them comes from historical research luminaries. So if you say, I'm going to discuss power, well, some of the stuff that I'll talk about actually, if you don't connect the dots, if you look at them independently, they come from Nobel Prize winners. Some of the stuff that I'll talk about in propulsion, not only is Nobel Prize winning, it's also from some of the earliest people that were scientists in the area of electromagnetism and motors and light, photons. So we'll discuss that starting next week. So all I'm doing is I'm repurposing and connecting the dots. But if you want to understand what's going on, that's kind of something you have to be into. If you go, what's this got to do with that? You're not connecting the dots. Or if you go, I understand what you're talking about, but that'll never work because it violates the current known laws of physics. Okay, in the last 10 to 15 years, there's been a lot of that where things that we used to have a good beat on are a little different once you start understanding quantum physics and start proving things out. There's a little latitude you have to add there because we don't quite know as much as we thought we did. So yeah, you have to envision where this is going to go over time, not what it was when they first thought about it. And yes, these are not going to be currently commercially at scale products. There won't be just go buy it off the shelf and push the button. There will be some initial, some smart startup is probably going to consider this and go create a whole new industry on it. And I won't be a part of that because I'm not going to spend the money and go through the effort to do it. I'm just there like poking things forward. So if you start with the premise that it's impossible or counters the known laws of physics, please look at contemporary information and then reassess your conclusion of impossibility. Considerable investment needs to be made before there'll be volume viability of this. There needs to be expenditures for trial and error and efficiency improvements. If you look back to the history of ion propulsion, almost 50 years ago, you'll find that when they first said, hey, maybe we can power a spacecraft with ion propulsion, somebody said, it's small fractions of a Newton of thrust. How will you ever power a spaceship with that? And then now any satellite that goes up that you want to be up there for quite some time, they're all ion powered. Anytime we want a spacecraft to go into deep space, or chase around a couple of comets or asteroids, they're all ion powered. So what you think might not be viable when you first get a good look at it, spend some money improving it, improving the efficiency of it, and maybe you need to do some nanoscale fabrication of it. But eventually it could prove out to be a solution provider. And if you think about, I'll wait until somebody invests the money on it. How many billions of dollars have been invested in fusion power? And it's not there yet. High energy particle physics, CERN, the Hadron Collider, and they're still investing money in it. And how much boondoggle money has been invested by the likes of IBM and Google and other companies in quantum computing. And they're just now to the point where they can get it to run for almost a full second. And it'll have qubits, maybe 100 of them. And meanwhile, we're talking about non-quantum computers that have terabits of flash and gigabits of RAM. And those are just normal things you can go purchase off the shelf. So initially, when something first comes out, it'll look totally implausible. But if you can connect the dots, if you can envision where it could be, if you just, had some faith, or as they say at the Los Angeles Union Station sundial, on the sundial, there's a plaque. It says, vision to see, faith to believe, courage to do. So there you go. That's what you need. So in this episode, to give you like a teaser bit, in this episode, we'll talk about power. So I went through the laundry list of problems with power generation. Yes, buying electricity is the dominant way of you getting power to power something. But you can only do that if there's a grid connection to where you want the power. And if there's no grid connection, you can't buy power. But if you're out in the middle of nowhere, if you're on the end of a long street, you're going to have to spend a couple of $1,000s to get the local power company to extend the grid from the main street to your house. But if you want power on a regular basis and you don't want to have to build your own power generation facility, You kind of got no choice. If you spend the money, you do it. I know somebody that lives in Montora Ranches out in the middle of the Everglades, and the street that was kind of the main thoroughfare wasn't paved, but it had power poles running down it. And Florida Power and Light said, you want power to your house? You're at the end of the street. You want it to be tucked away and isolated from everybody else? That's going to cost you $1,200 to get them to run just for you power down to the end of the street. Had no choice, had to pay it. So if you said, no problem, I'll go buy myself a generator and I'll install it myself. Oh, no, you don't. If you live in a place where there's a building zone and a building permit and rules for what you can build, you'll find out that the commercial off-the-shelf systems, the COTS, and the do-it-yourselfer stuff for electrical power for your home, where there is a grid, is something that's verboten. You're not allowed to do that. The building codes and your local building association or city will not let you do that. You have to go pull a permit, have the city justify that what you want to put in will match code, and then you have to go find yourself an approved vendor, installer that will install it for you. So your inexpensive off-the-shelf solution for do-it-yourself power that might be solar or wind suddenly is going to be quite a few $1,000s more expensive than you thought, because they want to push you back to grid power. How do they do that? Well, they work with the local city government. In the city of Fort Lauderdale, it was very funny. You can get a permit for free. The permit won't cost you anything if you want to put solar panels on your roof. But the only way you can get a free permit is if you use a city of Fort Lauderdale approved vendor, which is going to charge you a couple of $1,000 install fee for the $10,000 to $15,000 worth of solar power generation. So yeah, it's almost priced against you wanting to do it. And I think that's their point. If you want to generate your own private power, there's Florida law that says you'll have dual metering, because there's a presumption that you're going to be generating more power than you need, and you're going to want to have the power company kind of pay you back for it. But they don't really pay you back for it. What they'll do is they'll take your excess and credit your bill, and then once a year, if at the end of the year you still have a plus on your credits, then they'll credit your account with money. They won't actually pay you for it. They'll just credit your account for next year. They used to actually pay you for your excess on a monthly basis, and they were, FP&O worked with the state of Florida Public Service Commission and said, that's a lot of money because lots of people are putting in place power. So they found a way to stop that. And it turns out that if you want to save money on your solar or wind power installation and you put in too little power, you'll never get your credits and the system will never pay for itself. If you put in too much power so that you'd always have an excess, the state of Florida will label you as a commercial electrical service provider, and you'll have to go through regulatory and licensing expenses. So if you say, I've got a big enough area, or I can put a big enough generator in, I'll generate 0.5 megawatt. And they'll say, oh, that makes you a commercial producer. You're not allowed to share that with anybody else in your neighborhood because licensing won't let you. And how do I know this? Because I know somebody who tried to actually do that. They tried to form their own co-op, pull together the money, put in a megawatt power generation facility out in Weston, Florida. And they were shut down very quickly. So too little, and you don't generate enough to get credits to cover your costs. Too much, and you're a commercial producer, which jacks up the price. So generating your own power when there's a local grid is purposefully made where you're not going to do it. And like I said, the permit costs are artificially low to stimulate contractor revenue. But when the grid goes down, unless you supply your own power, you're not going to have any power. So I, at my house, have a 2000-watt Honda generator, and I only run it when I need some juice when the power's out. But how long is that going to last? Well, I bought the extra tank, and I can get 8 hours of gasoline power off of it. But beyond that, I got to go hunting for a gas station. I could have bought a natural gas fired or a diesel fired generator that would cost me, $15,000 to $20,000 for the generator and the install and the FP&L hookup. But that's only going to last maybe 3 days tops. And then I'm out looking for a diesel supplier or a natural gas supplier to drive to my house and refill me. So that's impractical. And if I say I'll have solar panels or a wind generator, if there's not enough sun or no sun, or there happens to be a low wind day, I'm reliant upon whatever amount of batteries I put in. So that's kind of not really getting you there. And when there's no power source, it's going to exhaust your battery, and how are you going to get it recharged? So these are almost solutions designed to not really solve the problem, but to give you a stopgap. And for the bigger solutions, there's those problems. What if you have a ship, you want to transport some cargo around the world? You're burning fuel oil or diesel. You're polluting the air and water. And it's actually more expensive than that. It's a cascade. So when you dock your ship, either a tank truck or a series of tank trucks or plumbing has to deliver your refuel to your port. So that limits your total nonstop travel distance, because sometimes you have to put into port just to refuel. Well, if you say, I'll go with nuclear powered ships like the US military, I'll have steam driven turbines. But every 3 to 5 years, those require the fuel rods to be removed and disposed of properly, and then new fuel rods put in. Well, that generates waste, and it takes the ship out of service while you're refueling it. And there's always the concerns over fission reactor safety. Well, if I've got solar panels on Earth or in space to power my power plant or my spacecraft, the efficiency is not that great. It's maybe about 20 to maybe 30%. They degrade over time. You don't get the same amount of power out of your solar panels at year 10 that you did at year 1. If you're not cleaning your panels on Mars, as we saw with the Mars InSight lander, you're toast because it got covered with dust. Large arrays like you see on geostationary satellites are targets for solar wind and micrometeoroid damage. So they're not going to last a long time. Some of these space probes that have lasted the longest use radioisotope thermoelectric generators. They have refined plutonium on board. It's not a fission reactor. It's just producing about 400 degrees Fahrenheit of heat for several decades. And, you have your concern over the plant that generated the refined plutonium generates its own waste in the process. You have the concern over what happens if your rocket goes boom when you launch it. Is that going to rain plutonium down over people? Once you get it up there, the thermocouples they use for generating the power, they degrade due to neutron decay over time. So if you said, Voyager 1 and Voyager 2, are they producing the same amount of power they did when they launched? No, they're producing about 1/10 the power as when they launched. So they can't turn on all their instruments, which is why neither one of those probes have taken pictures in decades. Not because the cameras don't work, it's because they don't have the power to do it. Imagine train engines, freight trains or passenger trains. They burn diesel, or the latest freight trains on the CSX line burn natural gas. But the actual driving is done by electric motors. So if you can't see it in the sky, the natural gas does pollute the air. It's CO2. And if they're still burning diesel, you can certainly see that. And once again, it's a expensive cascade for refueling. The train doesn't go to Port Everglades to be refueled. It has to have fuel lines come over to the train depot to refuel the trains. If it's natural gas, the same thing. You have to have natural gas pipeline or tanker trucks come over and refuel the train. And that limits the total range and the maximum load carrying capacity of the trains. Subways and trams and trains, they're all running using electric motors. Even the ones that are not running on natural gas or diesel, they have a pantograph on top of the cars. So you have to have an infrastructure of overhead wiring. And you may think that they're running directly off that, but they actually have batteries on board the electric trains because sometimes there'll be a gap. Think about if you want to take a train track in a circle, oh, you can't join the wires together because that would be a dead short. So there's a gap. So as the train goes over that gap, it loses power. It goes on battery power for a few minutes, and then it goes back on overhead power and recharges the battery. Once you start digging into these things, you can find their Achilles heels. And there are actually trains now that have batteries on board, and they use them in freight switching yards. They're green trains. You know, they run on lithium batteries, but something's got to charge them up in between time. And for that, there's no solar panels at the freight depot. They charge up on the grid. So you're still stuck with the grid. So if we wanted a better solution, what would we be asking for? What would be the requirements? Well, I'd want an infinite source, no fixed fuel, nothing requiring resupply, no moving parts, no recurring maintenance. It needs to be a reliable source with no outages, no coverage gaps. It needs to not be reliant upon sunny days, windy days, river water, or tides. It must produce power day and night, 24/7, 365. It must be usable at all latitudes. I don't care what your sun angle is. And it needs to be usable in urban and rural areas, even where there's trees and where there's no grid. I don't want to have to pay to have a grid run to it. And I don't want any commercial metering. I'm not planning on giving any back to the local grid, so I don't want any dual metering requirements. I want to completely cut the cord with commercial providers and fuel suppliers. I want to eliminate the need for a fuel supplier to make a delivery or pipelines. You know, if I'm running my generator off of natural gas and I don't want a delivery truck, that means I have to have natural gas pipelined to my house. Don't want that. I'm not going to be running it off of radioactive materials because that's, radioactive waste in both fuel production and use. I just don't want that. I don't want a high-priced installation or, contractors that work with the local government to make sure there's a good, healthy markup for them. Any batteries will not be for storage capacity. They'll be for basically a momentary ride through if needed, or a surge buffer. And I need a unit that will produce what we think of as grid power in the US. Two-phase, 120 volts AC, 60 hertz frequency, and I'd like it to be about 12 kilowatts worth on a regular basis and about 100 amps. 100 amps may not sound like much, but if you were to buffer your normal load in your house, 100 amps is a lot because your typical 3-2 house, 3-bedroom, 2-bath house, if you don't ask for more power, they'll put 130 amp service breakers on your house. When I bought my house so many years ago, I said, no, I'll pay extra. And I paid, I think it was $700, cheap back then. And I got 200 amp service to my house. I rarely, if ever, will need it. But if I ever need it, I don't have to get new grid tie connection, which by today's prices will be a lot more expensive. So if I need 220 or 440 AC, I'll do what they do in homes. If I have 120, it actually brings in two-phase 120. So I join two phases and I get 220 to run my air conditioner or my range or my oven. They can do the same thing. If it's a commercial site and they need 440 for running machines or heavier air conditioning units, join up a couple of generators and you get 440. So I think, 1 unit would be good for most homes. 4 units would be good for your typical size business until you get to industrial scale. And if 1 to 4 is possible, make it 10. But what? What is going to generate this power? I'm asking for a lot here. Of course I am. It's me. So what kind of source can I get for this power? Well, it'll be from the sun, but it won't be photovoltaic like solar cells. It'll be from solar electron neutrinos. And we'll get into that whole physics problem with neutrinos, but they're already getting past that. Solar neutrinos will exist so long as the sun exists. That's an inexhaustible power source. If the sun no longer exists, you've got a bigger problem to solve. So the Earth is bathed in solar electron neutrinos 24/7, 365 at night, regardless of clouds, fog, or rain. And it doesn't matter if it's nighttime, the neutrinos go right through the Earth like it's not there. You don't need to face the sun. The U.S. Department of Energy Fermi National Lab states that there's about 1 × 10⁻¹1 solar neutrinos striking every square centimeter of the Earth 24/7. That's a lot of neutrinos. But since neutrinos have a neutral or no charge, they don't interact with much. So we don't think of them as a source of power. But they're moving at near the speed of light. So they have momentum. And, they're hitting the Earth regardless of your latitude. So they're accessible anywhere on the Earth, no grid required. So what we need is a way of tapping into that. Because once we can tap into that to at least that minimally required level of power, we have an inexhaustible, no nuclear fuel needed, thank you very much, no solar panels needed, thank you very much, power source. And if you create something that's modular, you can build it to what scale you need. So that's what we'll get into. So what about these neutrino thingies? Neutrinos have been proven to exist. The Greek symbol nu, which looks like a lowercase letter v to me, is actually the symbol for neutrinos. So if you ever see in physics papers this reference to a lowercase bolded v, it's actually the Greek symbol nu, which refers to neutrinos. Neutrinos come in different flavors. Now, they're not actually eating the neutrinos, tasting the flavor of them. It's just different kinds of neutrinos. There are electron neutrinos, muon neutrinos, and tau neutrinos. And electron neutrinos that we get from the sun, those are very high in density and occurrence. Muon neutrinos, less, and tau neutrinos, even less. But as you go to muon and tau, they're far higher energy, but they're coming at very infrequent rates and densities. So we'll now not count on them. We'll just count on the from the sun solar electron neutrinos. It's been proven that neutrino flavors change on the fly, except a lot of times they go from being like muon or tau to being electron, which means that even the ones that are less frequent, that have more energy, when they flip down to electron neutrinos. So it makes even more electron neutrinos. But the concept of taking something from high energy to low energy, that flip implies that you have mass by way of energy. Mass and energy are actually related. Neutrinos come from different sources. You can actually have neutrinos from fission reactors. And we'll discuss that aspect of it momentarily. But you can have neutrinos from reactors, but we're talking about the neutrinos from the sun, the solar neutrinos, and a particular flavor, the electron solar neutrinos. We're not talking about the ones that come from other sources in our galaxy, other stars, or the ones that come from very bright radio stars that are giant black holes in other galaxies, the galactic ones, because they may be much higher energy, but they're few and far between. There are also the flip side of neutrinos, which are anti-neutrinos, or neutrinos that are really not interacting with anything. They refer to those as sterile neutrinos. But anti-neutrinos are fleeting. It's very hard to actually produce those except in particle accelerators. And sterile neutrinos are, we've not found an abundant source for those, so I'll just say those are not usable. But as to neutrinos having flavors and flipping, and that relating to mass, that's actually the Nobel Prize in Physics for 2015. So I'm not just, as the saying goes, speaking out my derriere. There's actually Nobel Prize winning physics that says neutrinos have flavor. And the electron neutrino has mass, and there's a relationship between mass and energy. So neutrino sources identify themselves by their electron volt values. An electron volt is a very, 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 very small value. We'll discuss how many regular old-fashioned volts there are, or how many electron volts does it take to make a real old-fashioned volt. And it's a lot. But the electron volt value goes up as the source becomes more distant, but the probability of interacting with them goes way down. So we'll not count on the galactic or extragalactic ones, just the solar electron neutrinos. And when an electron neutrino interacts with something, it transfers its energy to an electron. And if allowed, the electron that gets charged up will want to release that energy as a photon, as a particle of light. And this is where reactors come into play, because if you've ever seen that blue glow from the water vat of a fission reactor, that blue glow is called Cherenkov radiation. And what's actually happening there is the neutrino is energizing an electron, and the electron produces a photon, and as the photon gets emitted and slows down ever so slightly as it transitions from the energy absorption rod of the reactor, the neutron dampener of the reactor, to a photon, and the photon encounters the water, which has a different index of refraction. It produces a secondary photon, and that particular secondary photon, for the type of neutrinos that are emitted from fission reactors, results in deep blue photons. So that's what you get. You get Cherenkov radiation, which is deep blue light from fission reactors. And it's coming out of the neutron bombardment of the radiation dampening rods. And when we talk a little in a few minutes about what are those rods made of, why do they generate electrons when they get encounters with neutrinos? And do they get a lot of them, or do they get rare encounters? Because most of our neutrino detectors don't detect very many neutrinos. But the rods they have in fission reactors, they see a lot of neutrinos. In fact, they degrade over time and have to be replaced. So our detectors don't see many neutrinos because we're looking for those blue photons. But the rods in reactors see lots of neutrinos. So we'll be.
I didn't understand. Can I ask a quick question now, or should I wait till
you can ask right now? Go ahead.
So are you saying it's neutrons or neutrinos traveling faster than the speed of light in water that generates the Cherenkov radiation?
The neutrinos interact with the material in the rod. The material in the rod produces an electron in the rod. The electron in the rod, being charged up, wants to discharge the excess energy as a photon. It discharges the energy as a photon, but the photon on its way into the water that's in the water bath of the reactor slows down. And when a photon slows down, it produces a secondary photon of a specific wavelength, and that's where you get the blue glow of Cherenkov radiation.
Yeah, we all know that. It's just, it's a photon generating a secondary photon.
Mhm.
It isn't a neutrino being generating it.
No, the neutrino generates the initial electron.
And does the neutrino always generate the initial electron,
Yes,
or only sometimes?
yes,
Always.
yes,
So why can't you use the cadmium rods for capturing solar neutrinos?
because they don't use cadmium anymore. They're
So what
swapping
do
out,
they use?
they're swapping out the rod, the dampener rods in contemporary reactors, in these new modular reactors they're building, because the material they used to use, they've tried a number of things. They've tried cadmium and boron and a number of different materials, and they all suffer from neutron damage. Neutrons are neutral particles, but they can play hell with the materials because they're generating so many electrons that the electrons literally rot the rods. So they have to find new materials, and they have a new material. And we'll get into that. But if you're looking to detect neutrinos from space, they're not doing it the same way that reactor dampener rods are doing it.
Right, why not?
I don't know why not. It seems quite obvious to me that if you want to get lots of neutrinos, and we're already doing that in reactors, why not copy that solution and generate your, the fission reactors have an enormous blue glow. Why don't you use that? And they do. I was actually able to chat questions to a presenter who was discussing the ice neutrino detector at Antarctica, and I was asking, well, why don't you use some of the other means of detecting neutrinos? And it was basically, we got what we got. We built it a few years ago. We sunk it into the ice, and the ice is frozen in place. And it's now called the ice cube neutrino detector because it's one giant ice cube. And the next time they build one, they might do it differently. But right now, they got what they got. So they don't, they detect maybe 200 to 500 neutrinos per year. And that's just way too few to generate electrical power. Okay.
Yeah, what you?
The ice cube. Yeah. So what do we want to do with the neutrinos? We don't want to accelerate them. We want to concentrate them. We want to increase the number of neutrinos that are producing electrons.
Hello? Somebody interjected about the ice cube. Did I miss something?
Yeah, a couple of weeks ago, we were talking about the ice cube in a news article. In Antarctica, there is I think it's 1 square kilometer of Antarctic ice that contains a few thousand neutrino detectors. And what they're looking for is, as neutrinos come in through the body of the Earth, they will strike basically water molecules in the ice and cause secondary blue photons as the initial electron transition generates a secondary photon that slows down in the ice of the water, which has actually got a different index of refraction than does sterile water. So it actually produces a slightly different color blue. But that's all they're picking up is those blue photons. So it's very passive, not aggressive. So they generate between 200 and 500 of those blue glows per year, which is way too few to be usable as an electrical power source.
Why did they pick to put it in ice? I mean, got water in other places. And
because it was much easier to suspend their detectors in frozen water, and frozen water has a much different index of refraction than does ocean water. There is actually in the Atlantic, not too far off the Azores, another neutrino detector that their detectors are literally on strings down into the ocean water, trying to pick up the blue glow in the ocean water, and the ocean water is not cold enough and not sterile enough, not pure enough, so they get even fewer. They get maybe 30 to 50 neutrinos a year. So they literally, in the Antarctic, melted holes in the cleanest, pristine part of the ice. And then they quickly sank these vertical lines of detectors down into the hole. And the hole rapidly filled up with water that then froze. And now the detectors are frozen as a vertical string of detectors. And they drilled several thousand of these holes into the ice, sunk in the detectors, and then the detectors froze in place. And now they have this 1 cubic kilometer of detectors. And that's how they detect neutrinos. But it's very passive. Neutrinos don't have a charge. So they're not positive and they're not negative. So you can't take an electrical field and draw them in or push them away like a particle accelerator. The reason why particle accelerators love to accelerate protons is because they can use electromagnets. Because the positively charged protons are pushed or pulled by the electromagnets as they switch polarity. But you can't do that with a neutrino because neutrinos don't have a charge. They're not positive, they're not negative, meaning you can't steer them, you can't concentrate them with an electric field. But because they're moving at nearly the speed of light, they have a usable momentum based upon their energy. There's no requirement to accelerate them further. They're going fast enough. What we do need is to gather more of them in a smaller area, but we're not going to do it by steering them. If you've ever understood how an X-ray machine works, they have electromagnetic plates that actually steer the electron beam to focus it onto a target and accelerate it. But we're not looking to do that because that won't work with neutrinos. But neutrinos do have a small number of electron volts that are related to its mass, which is minuscule. And different types of neutrinos, different flavors, different sources have different electron volt values. The solar electron neutrinos have a good amount of energy. They're moving at almost the speed of light, and they have a quite high density or flux. So those are the ones we're going to focus on. But if you think that it's impossible to concentrate neutrinos because they don't have a charge, we actually have satellites in space that image in gamma rays. And gamma rays are also absent a charge. Cosmic rays do have a charge, and they actually use electrical fields to get rid of the cosmic rays because they just want to focus on gamma rays. There's a space telescope formerly known as GLAST or GLASS that has been renamed the Fermi Gamma Ray Space Telescope. And what it uses is high mass plates. So what it's got is it's got little grid plates that are made out of high density pure tungsten. And tungsten is a high density heavy material. And what happens is the gamma rays, which do not have a charge, are actually drawn by the increased mass of the tungsten. So here you have gamma rays flying through space. They come in through the front of the gamma ray telescope, and they are drawn towards the high density tungsten. It doesn't attract them so much as, think of it as the moon orbits the Earth because the Earth has a much greater mass and bends space-time, so the moon orbits the Earth. Well, the Earth orbits the sun the same way. The Earth has a much more minuscule mass compared to the sun, and yet the Earth is drawn to and orbits the sun. Same thing we're looking at doing here. If the Gamma Ray Space Telescope can concentrate gamma rays by way of a high mass target, why don't we do the same thing for neutrinos? Neutrinos have a very tiny mass. What if we had a very high mass that we use to draw them in? So that would be our concentrator. We'll just use a high mass. The neutrino-electron interaction will transfer energy from the neutrino to an electron. we're not going to let it become a photon. We're actually going to transfer away the available electron before it can become a photon. So we catch it before it glows, basically. But first, you have to understand why things glow. And to get into that, we'll learn a little bit about the material in blue LEDs. Light-emitting diodes, or LEDs, are nothing more than fancy semiconductor junctions. Now, what semiconductor means is you have something that is not a conductor, like silicon, it's an insulator, but you chemically stir in other materials when you're cooking up the silicon crystal. You dope it, and depending upon what material you dope it with, it either becomes an N or a P, meaning it has either electrons, it wants to give up electrons readily, or it has places to receive electrons, nicknamed holes. So you have an N type that generates electrons, and you have a P type that wants to receive those electrons, and then between the two layers, you have a small gap of silicon. And the small gap of silicon has something known as a band gap. And if the band gap is wide, you'll get higher energy photons out of this junction, out of this band gap. And they found that, well, we could generate red LEDs because we figured out the chemistry for the N type and the P type and how big the gap's going to be. And that dictated, good, we got red. We did the same thing with slightly different doping materials and we got green. And now we need blue. It took them a number of years to figure out the correct chemistry for the N type and P type to get the band gap wide enough for them to generate photons with enough energy, a short enough wavelength, to make it spit out blue photons. And the 2014 Nobel Prize in Physics was on the team that fabricated mass-produced blue LEDs. And that's when you could have LEDs that were RGB. And when you mix RGB together, you get white light. So whenever you see those inexpensive electronic devices, and they've all got god-awful blue LEDs on them that keep you awake at night, it's because the blue LEDs are actually cheaper to make than the red ones or the green ones. So that's why everything has blue LEDs in it. The particular material that they used in the junction was not silicon. It was something called indium gallium nitride, chemical formula INGAN, or the basis of it was the gallium nitride, the GAN, because it has a wider band gap than the silicon they were doping before. And you might see some videos on YouTube about silicon carbide being all the rage. Silicon carbide is kind of a stopgap, and the next more capable LED technology and formulation will be from indium gallium nitride. If you think that blue was kind of how low can you go, they've actually gone better than that. They changed the doping agents, and now not only do we have red, green, and blue, but we have deeper blues. We have violet, which is actually purple. That's the color Blu-ray players use. And we've gotten all the way down to LEDs that are at 222 nanometers, which is well into the invisible ultraviolet C band. And they use those for germicidal disinfection. And where we've seen a lot of that recently is hospitals sterilizing operating rooms using UVC light that is so deep in wavelength, it actually ruptures biological cells. So if we're looking to generate photons from electrons, and we want the highest possible energy output, the clue here is indium gallium nitride. But you don't have to make an LED, and you don't really have to dope it for both N type and P type. You can just pick one side. So we'll get to that in a moment. So we know we don't want to waste our neutrino interaction on generating blue photons. And we know that contemporary semiconductor materials can take those electrons and generate them, can produce electrons from it. So if we want to generate the electrons, now we need something to carry away the electrons. And let's say we only doped the p side. So we have our holes. We have something readily wanting to gather all those electrons and conduct them away. But now we need something for the other side that says, I'm eager to give up electrons. So we're going to take a layered approach. We're going to have 3 layers in our semiconductor that generates the electricity from neutrinos. We're going to have a generation layer. We're going to have a transference layer and a concentration layer. The generate layer is going to produce those electrons. And once it's got an abundant amount of electrons, the next thing we want is something to suck away those electrons as fast as possible. And then we need something to draw the neutrinos in, to concentrate them onto our generator cell. So it's very typical that semiconductors, when you're building integrated circuits, you might have a couple of different types of chemistry in the chips, but the amount of any particular material you're laying down is going to be very, very small, because the transistors are little tiny, nanometer sized, billionth of a meter sized islands that are layered and adjusted and connected. But this is going to be different. This is a layer is an entire coating over that layer. So if you happen to have a generator that's 1 square centimeter, the entire square centimeter is going to be a generate layer, a transfer layer, and a concentrate layer. So it's going to be very high in generation capacity. And if you need bigger generation chips, just talk to the people that fabricate semiconductors, because they're now up to very, very big, hand-sized semiconductor dies before they slice them all up. So, if they can generate a disk that has the 3-layer material, that would be a very large generator. But you don't have to do that. You can generate individual chips. So the generator layer, what we need is something that would really, really like to spit out electrons if it encounters a neutrino. There is a material that really loves to give up electrons. It's called lithium deuteride. Lithium deuteride is lithium hydride, but the hydrogen part of it is deuterium, as they use in, oh, look at that, heavy water reactors. Sometimes they refer to this also as lithium-7. So you might see it commercially referred to as lithium-7, but it's lithium deuteride. It is highly reactive. You don't want to get it anywhere near water itself. They use this stuff in fission reactors because it reduces the speed of fast neutrons, particles that don't have a charge, neutrons. So they use this material in interactions, and we can use that in solar electron neutrino interactions. The material has considerable density. It may only be a small molecule, but you can pack them in really tight. They don't interact with themselves. They like interacting with other things. So you can pack them in really tight and get a good density. So just a few nanometers of this material would be okay. And much like you build semiconductor LEDs, imagine if you just built 1/2 of the LED. So you're building only the N layer or the P layer. And you put the generator layer directly in contact with the transfer layer. So any electrons in the generator layer that are produced from interactions with neutrinos immediately generate electrons that are immediately sucked away as fast as possible. Lithium deuteride is highly reactive. If you add the dust of lithium deuteride in air, it will find the moisture in the air and explode. So you want to vapor deposit the lithium deuteride onto your transfer layer and then quickly encapsulate it before you bring it out of vacuum so that it's sealed off from outside air. The neutrinos won't care about that insulation layer. They'll go right through that. So that is our generator. This is what takes in the neutrinos and generates electrons. Now we need something that once all those electrons are being generated, we need something to be sucking those electrons out onto our power destination. So we need something that has very poor electron material. So it's readily acceptance of generator-produced electrons. It turns out, oh, look, here's where our friend indium gallium nitride comes in. If you take indium gallium nitride and you dope it, or you chemically taint it with a little magnesium, just a touch of magnesium in the formulation of the crystal, it becomes a p-doped magnesium indium gallium nitride. And the U.S. Army Research Laboratory has experimentally tested the gallium nitride, and if you give it electrons, it will want to get rid of the electrons at 1.9 times 10 to the 7th centimeters per second. So it very quickly wants to, like, you give me an electron, I don't want to get rid of it. It will conduct it away very quickly. And if you said, well, how much electricity can I conduct away from this particular material? 225,000 volts per centimeter. So it has a lot of holes that it wants electrons in, and as soon as you put an electron in the hole, it wants to conduct the hole away. It wants to conduct the electron away. Now here's where you get to the measurement. One, as we know it, volt is an electromotive force of 6.24 times 10 to the 18th electrons. Think about the numbers for a second. If I wanted to generate 1 volt, I need to be producing 6.24 times 10 to the 18th electrons. But notice that gallium nitride can do about 225,000 volts. So a small amount of indium gallium nitride is going to be able to conduct away a lot of electrons if the generator generates them. So we have no problem transferring the electrons out. We have a mechanism for generating the electrons in when they interact with neutrinos. And if you sort of doubt gallium nitride, there is a kind of transistor that whenever you look at your phone and your phone has a super fast charger on it, that super fast charger is courtesy of a kind of transistor called a high electron mobility transistor, and it uses indium gallium nitride. The kind of transistor is called a HEMT transistor, because as you're charging up the lithium battery in the phone, it only wants to take in so much power instantaneously. So you're pumping it, but you have to pump it very, very, very quickly. So you go pump, 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 pump at a very high speed. And the only thing that can switch that much power that quickly is indium gallium nitride, or a HEMT transistor.
Well, obviously, we all know indium gallium nitride is going to be able for us to drain the electrons. The question is, how is it you were saying we were going to collect the neutrinos and convert them into electrons?
The previous slide. Let me go back to the previous slide. That's the generator layer. So the same thing they're using in modern reactors to receive neutrinos from neutrons and convert them into electrons, which produces the photons, which makes that lovely blue glow in the water bath of reactors. So we're using the same technology that they use to suck in as many neutrinos as possible in reactors. So we're just borrowing what they're already using. So there's going to be a high quantity of neutrinos that are going to be producing electrons courtesy of the lithium hydride. That's your generator layer. Now you're generating lots of electrons, but you don't want to have a band gap to spill them out as photons. You want to take those electrons and immediately conduct them away. So you need a transfer layer that will suck up as many electrons as you can produce. So here we have something that can do that. So you have
so it can't be just lithium hydride, though. It has to be lithium deuteride.
Yes.
Oh, I can't get that on AliExpress.
No, you can't. That's why, hey, the same people
Yeah,
that are
I can get
spending,
the lithium deuter. I'm already looking up the lithium hydride. I'm ready to order that, but they
oh,
don't have
lithium
lithium
hydride. Yeah, you
deuteride.
can, lithium hydride's expensive, but you can just buy that off of Amazon. But lithium deuteride, you can't.
No, no, I just looked.
Yeah, yeah. So you're going to have the same people that are spending $1 billion to study fusion reactors and give you just that little incremental improvement. Spend a few $1 million on this because
Adam, I'm getting
the,
this.
the technology is already there. So we've got our generator that's sucking in the neutrinos, producing electrons. We've got our transfer layer that is sucking in the electrons and conveying them away as fast as possible. Now we need something to concentrate the neutrinos. Remember, neutrinos are proven to have mass, but no charge. So we cannot concentrate them using an electrical field. But the 2015 Nobel Prize in Physics proved that neutrinos have mass. And we already know, much like the moon orbits the Earth and the Earth orbits the sun, if you have something with a really small mass and you have something with a really huge mass by comparison, it will be drawn towards it, even at the quantum level. So you need a material that is very, very high density, has a very much higher mass than neutrinos do. And that's something called osmium tetroxide. Yes, these things really exist. Osmium tetroxide has a density much greater than tungsten. So you're talking about the difference between 19.35 grams per cubic centimeter versus osmium, which has a density of 22.6 grams per cubic centimeter, which doesn't sound like much, but when we start scaling this up, it gets to be heavy. So you've got your generator layer, your transfer layer, and then beneath it, you've got your concentration layer that's literally applying a microscopic gravitational field to the neutrinos to pull them in. It's not going to accelerate them. It's just going to take the ones that may be a little off to the side and pull them into the generator. So it's impractical to presume we're going to get 100% of all the solar neutrinos that's hitting the Earth per square centimeter. But if we could shoot to just get 20% of that, a few nanometers thick layer of osmium tetroxide ought to be sufficient. There is a company already working on power generation from neutrinos. There's a whole website devoted to neutrino science that has a branch of that website that's all about how to generate electricity with neutrinos. Their shortcoming is they have no concentrator concept. They're just hoping the neutrinos interact with your material, and they're not even using lithium deuteride. They're just using a very reactive material. I think it's a sodium material, which sodium and lithium are both reactive. But they're starting, and this that I'm talking about here is kind of like the next level of optimization. They'll get around to it eventually, but only if somebody connects the dots. So if we said, I'll generate one of these cells, it's not going to generate much power, but I'll make one of them that's like a square centimeter and maybe 5 millimeters thick. That's one cell. How would I get more power out? Well, obviously, I'd join up a whole bunch of cells. If I have my individual generator, transfer, concentrator materials, and I make those into tiny cells, and then I join together those cells as layers of very large areas, I can now get millions of these cells per cubic meter. I interconnect all the individual cells. I then use a DC to AC inverter to stabilize the aggregated power. You remember me mentioning that galactic and intergalactic neutrinos exist, and they're very much higher energy than solar neutrinos, but they're very rare. But if we just presume that we're only going to get solar neutrinos into our generator, and all of a sudden an extragalactic neutrino comes in to our square centimeter, it could generate a little surge. It wouldn't last long, but it'll generate a little surge. So we need something that will buffer that as you aggregate this across a big brick of these things. And the way you do that is you convert the DC output to AC using an inverter so that the AC coming out is your 120 volts AC. So you now have an inexhaustible, as long as the sun exists, continuous, doesn't matter whether it's day or night, and you don't need a battery backup because it's never going to be without power. There are no moving parts, no lubricants, no consumable fuels. It produces no exhaust and has zero maintenance. It's not dependent upon sunlight, wind, waves. It's not blocked by clouds, rain, or fog. It does not produce a lot of heat as it charges up because the electrons are carried away instantly. So it doesn't need heat sinks, fans, refrigeration. There's no like steam high pressure water generator turbines, and it doesn't require critical cooling down to like, sub-zero temperatures. There's no grid connectivity reliance. You don't need any metering of any kind unless you want to measure how much is coming out of it. There's no requirement for sunlight access, so you don't need to put this on a roof. In fact, design it to be buried in the ground, because remember how the Antarctic neutrino detectors are not looking for the neutrinos coming out of the sky. It's actually looking for the neutrinos that have already come all the way through the Earth. So, bury this a few feet underground, and now you have something that has no maintenance, and it's not visible. It disappears. So when you build your house or you build your office building, just go, dig your parking lot or your driveway a little deeper and bury it down there. It's not a high cost to dig a ditch, not a high cost to dig a pit, and you drop this thing into it, hook it up, one-time cost to install, no monthly power bill. Yes, the materials are reactive. That's why you have to encapsulate them. It's not radioactive at all. It doesn't produce any toxic waste output. There's no exhaust fumes. You encapsulate the cells, and it makes this giant brick have high structural strength. So, even if you bury it 2 feet below your driveway or your parking lot, and then you drive something heavy over it, it's not going to damage it. So, yeah, but proof is in the pudding. How much power can you actually generate from this kind of thing? Well, let's do some calculations here. It's all in the math. So, one solar electron neutrino produces 1 times 10 to the 6th electron volts, which is 1.6 times 10 to the minus 13th volts. So this is one neutrino produces 1/1000th of a nanovolt, which is a billionth of a volt. So one neutrino by itself will not power anything. The occasional extragalactic neutrinos may be millions of times more powerful than a solar electron neutrino, but they are far too rare to presume you could ever get lucky and count on them to produce power. How many neutrino interactions will we actually need? 1 ampere is 6.28 times 10 to the plus 18 electrons per second. So we need 100 times that neutrino interactions per second per square centimeter. But we don't get that. What we actually get is, if Fermi Lab is correct, 1 times 10 to the plus 11 solar neutrinos per second per square centimeter. So we're going to need a square area, not one centimeter generator. We're going to need a square area that is 6.28 times 10 to the 9th square centimeters of surface area. That is enormous. But we don't have to do it all as one thin, flat layer. The neutrinos will actually pass through the material and we can actually do it as a series of vertical layers. So if we presume one generator cell is 1 square centimeter and it's 5 millimeters thick, and we can surface mount solder these things together serially and in parallel as a collective generator of volts and amps, then if you said, how about a single layer being 320 centimeters by 320 centimeters, that would be 102,400 cells. If I did 640 layers of that, that would be 65,536,000 cells. This would be a generator block that is 11 feet by 11 feet by 11 feet. It sounds huge, but it's going to be buried in the ground. Your car takes up more space than that in a single parking slot. Osmium is very heavy, so collectively this thing will be heavy. So bury it in the ground. The neutrinos will get to it. At peak efficiency, one block this size should generate about 134 amps. And it's not 200 amps, so it's not what I would want in my house. I'd need 2 of these. But 134 amps is nothing to, ignore. This is definitely power worth having. And this is the peak output. Solar is not really in bursts. It's continuous. If you occasionally want to buffer ride through, let's say, a burst, you get a gamma ray burst from a galactic collision somewhere, and all of a sudden you've got a few million extragalactic neutrinos that come your way that have 1 million times the power. You want a battery, not as an outage, but as a buffer to take in the extra power, store the extra power, and then drain it out at whatever load you're running. So if you go into your house and you turn on your oven and all of a sudden you've got a heavier draw, you'll be maxing out the power generation from the generator. And in the meantime, the generator will have charged up a battery so that you can run your oven for an hour, no problem. So if we have a buffer battery, which won't be that big, you could probably even get the generator down to 10% efficiency, which would be 67 amps. If you had a power source that was continuous 24/7, 67 amps, trust me, your house does not draw 67 amps continuous 24/7. So if you have a 67 amp generator and you have a buffer behind it that gets filled up, if you occasionally turn something on, leave it on for a while and turn it off, you're going to be fine. So how would this be usable? Well, it's certainly scalable. So you can make it bigger and bigger. You can also make it smaller and smaller. It all depends upon how much amperage you want out of this thing. I think once they figure out, look, this thing works, it generates power, they'll start putting it in things, kind of like they did with the radioisotope thermoelectric generators. They found out if I can have a long duration source of power, then I'll put that in my deep space probes. And I've got Voyager 1 and Voyager 2 that are almost 50 years old now, and they're still transmitting. But they're at 10% of their original power. If they could be at 100% of their original power, they might still be producing images of the nearest star much closer than they would be at Earth. It's a solution looking for a problem. And I remember when ruby crystal lasers first came out, and nobody knew what to use them for. And nowadays it's, oh, let's use a laser for that, for everything. So once you have an inexhaustible, highly reliable, non-fuel consuming power generator, it's going to find its own way into things. If, let's say, you want to colonize the moon or Mars, you send these things up in generator blocks because they're heavy, and you assemble them and bury them on the moon, and now you have power for your outpost or your city on the moon or Mars. And you don't need a silly fission-based reactor. You don't need a lot of solar panels. You don't need to be cracking CO2 to make methane, to burn methane. You don't need to be generating hydrogen to burn hydrogen. The power just comes on once you turn it on, and the power never stops until the sun goes away.
Question.
Yes.
You said we don't get that many neutrinos, and don't we have to have
No. We get a lot of neutrinos. Neutrino detectors don't detect many. There's a difference there.
Okay.
Yeah, there are a lot of neutrinos constantly going through your body right now. There's billions of neutrinos.
But don't we have to be able to detect them in order to utilize them?
Yeah, that's what the generator layer does. The generator layer will be the fast converter of neutrinos into electrons. The transfer layer will be the fast transfer layer to take those electrons, and instead of producing photons of light with them, get those electrons out of here. So you've got a generator layer, a transfer layer, and then the concentrator layer is the osmium to suck in more neutrinos.
Right now, something like this would cost a massive amount of money.
Will it cost more than the billions we're spending on fusion? I don't.
Well, you mentioned earlier, yeah.
I think this will be far cheaper and far more readily into commercial production, because the underlying chemistry is already proven and there's Nobel Prizes to point it out. So it's just connecting the dots. So somebody just needs to go do it, please. So once I post this to YouTube, we'll see if anybody else out there goes, taste the soup. Aha, they can make different size generators for space stations or for deep space exploration craft. They won't need solar panels, which degrade over time and are damaged by micrometeoroids. They won't need the radioactive plutonium. They won't have the radioactive plutonium generators suffering from neutron damage. So they get 10% of their power output 4 decades later. It's an inexhaustible source of fuel for power. So you don't need any refueling stops for, fuel oil or natural gas or any of that stuff. It's always charging. Let's say you took half the weight of the lithium batteries from a car and you put in a neutrino generator. The batteries that today weigh 3,000 pounds, you go, okay, let's have 1,500 pounds of lithium battery and 1,500 pounds of power generator. You would literally have a car that you could drive to work, and while the car was sitting in the parking lot, it was recharging itself from neutrinos. And then you drive home. You have a car that would never need recharging. Or any place where the power weight ratio is not an issue, like semi trucks. If you had 3,000 pounds worth of neutrino generator for your semi truck, you would never need to stop and get your truck recharged. So it wouldn't be, I've got a 500-mile semi. No, I've got a semi I never need to make a refueling stop. So then your limitation would be, how long is your crew going to be allowed to be awake and driving? That would be your limitation, is people. And as soon as you got autonomous driving for your semi, it'd be like cross-country delivery of goods. No driver needed, no refueling stops. Ships at sea. You could have your aircraft carrier that instead of every 3 to 5 years needing nuclear refueling, putting it out of commission, it would just have a big neutrino generation block. And instead of using the heat of a fission reactor to produce steam to drive turbines, your turbines would be electric motor driven. They have instant torque, much like electric cars do. So you wouldn't have all of the calcium and rusting that you get from seawater trying to heat that up to make your steam. So you could have a ship that would last longer and wouldn't need putting into port for downtime for refueling. You could have trains, trams, subways, and buses that need no third rail and no overhead pantograph, no infrastructure wiring. Then the only time you'd need to stop your train is to pick up or drop off passengers or the food the passengers eat, the water the passengers drink, or the freight you're hauling. You could have a train that literally could drive cross country, and instead of you having to make stops to refuel or switch trains, the train could just literally drive for days. So you could have an express train that would take you from New York to Los Angeles in 4 days and never stop. So you need to carry more food on the train. So this is a power generation solution looking for work. We'll need to connect the dots for future presentations. So once you have your inexhaustible, high longevity, nil maintenance power supply, it'll be a solution looking for problems, not a problem looking for solutions. So once you have open-ended electricity, the next thing we'll focus on is open-ended propulsion. Right now, everything we launch, every kind of rocket we launch is chemical-based. It's going to be burning through some kind of fixed tank of fuel. It can be a gas, a liquid, or a solid. But once it runs out, it better be going as fast as it ever hopes to be. Otherwise, it's going to be falling back to Earth. It could certainly make use of an inexhaustible power source. So then a rocket wouldn't have to be enormous, and it would not have to go as fast as possible, as quickly as possible, and then run out of fuel. Satellites, particularly satellites or deep spacecraft, could last far longer than a handful of years. Deep space missions could operate at full power, unlike RTG-powered ones. If whatever the propulsion source is was cumulative over time, kind of like ion propulsion, but without a fixed fuel supply, if it was cumulative and the spacecraft was autonomous, you could now start talking about uncrewed spacecraft with no people on board that could fly over generations to other stars. So we could send a robotic spacecraft to the nearest star in 30 years instead of 100 years. But we'll talk about that in the next presentation. Right now, just think of it as if you had inexhaustible power that you could scale up, and you wouldn't need any grid, and you wouldn't be paying, the proverbial Florida Power and Light every month, what kind of things would be accessible to you that aren't now? What kinds of things would you no longer need to do? So in conclusion, this series is going to identify and solve problems through the application of technology. Sometimes it'll be connecting the dots. Sometimes it'll be, why hasn't anybody done this before? Think about it for a moment. Does Florida Power and Light have a vested interest in creating a power generation solution that obfuscates the need of Florida Power and Light? No, of course not. Neutrinos are an abundant, inexhaustible source of power. They have no charge, but they do have mass, which means they can be concentrated by a denser mass. You can transfer excited electrons rather than having them generate rare photons. Solar electron neutrinos can be mass fabricated the same way that semiconductors can. If you build a giant block generator, you can sink it into the ground and it will produce, small business or household grade electricity 24/7, 365, no metering, no grid required. No moving parts, no fuel costs, one-time simple installation, nil maintenance. If you want to handle surges and use even a smaller generator, you can add a battery. But the battery's not there for sustaining through outages, much like your home UPS is. It's literally, I'm generating more than I need right now, store some of that, because if later on I want more than I'm currently generating, you can add in the battery. They should be spending a fraction of what they're spending on fusion research to research neutrino power generation. The problem is, if they actually did it it would take too much revenue off the table from too many sources. Everybody that wants to make money off of you in the renewables energy market might not get any money off that table because it's not there anymore. No grid, no solar panels, no windmill generators, no big UPS batteries. How are they going to make any money? So if a solution was provided where they weren't going to make that money, they just wouldn't do it. We don't need to generate huge power plants if everybody has their own power plant. Back in the day when I was growing up in South Florida, a lot of homes had solar hot water heaters on the roof. This is just an array of copper pipes that were covered with black tar paper shingles put inside glass, and you'd pump water through it, and it would generate your hot water. And you take the hot water and you put it in a tank. And you never needed electricity to produce your hot water. The cost of them went up, and when a hurricane comes through, they get damaged, and so they fell out of favor. But you can still put those up there if you want to. Well, think about it this way. What if you could generate electricity to heat your water and you weren't paying FP&L, and you could bury the electrical generator in the ground where it would never be affected by a hurricane? Oh, there you go. Well, what if you could produce your electricity, and unlike solar panels on your roof, you weren't drilling holes in your roof which might leak or be damaged by a hurricane or a tornado? Your power generator is buried in the ground. It's not going to be affected by bad weather. Yeah. Who wouldn't want that? Yeah, but all the guys that are making money off of that, they wouldn't be making money off of that anymore. And things that exhaust their fuel, like, anything that runs on fuel that has to be refueled. If you no longer need to be refueled, think of it this way. All those truck pit stops that you see with the restaurants and the overnight sleep areas and local hotels and, train depots that have local, Motel 6 kind of hotels. If you don't need any refueling and you don't need as much maintenance, you may not need as much of that. So they have no vested interest in, you putting their pit stops out of business. So yeah, maybe it's possible to do this. And the reason why they don't look into it is it might be too good of a solution. It is too big a paradigm shift for too many people currently taking money off the table. Of course, that's just my opinion. I could be wrong or right. And if you want to know more, there's information on neutrinos and the Nobel Prize in Physics for 2015. And if you want to learn about ice cube and neutrino detection, you can learn about that. And if you want to learn more about, there are people out there spending probably handfuls of millions per year on developing neutrino power generation. Too far-fetched?
Seems far out.
Yep. Just connecting the dots.
Futuristic.
Okay. We're past the bewitching hour.
Oh.
All I can say is, gee, I've had fun. Anytime anybody wants all the stuff that you see on these presentations, they're actually a PowerPoint. I'm not like reading notes. I'm actually reading slides with pictures and stuff like that. And so if ever you want to give the information to someone, just shoot me an email and I can email attach you the PowerPoint. It won't have my sterling dialogue, but then, a lot of people just say, you're just reading the bullets. Now, I'm throwing a few words in here and there, and sometimes to speed things up, I might paraphrase, but that's the information. And all the hyperlinks are active. So, yeah. Okay. Any comments or questions before I stop sharing?